Here we are again, lecture number 2 about astronomy, descriptive astronomy. This lecture is going to cover most of the material in chapter 5 and 6 of the text. And in short, that's about the kind of stuff that astronomy looks at, uses to analyze the celestial bodies, that being radiation, electromagnetic radiation, light, and other kinds of electromagnetic radiation. And then a little bit about the kinds of instruments that astronomy uses to collect that radiation. Alright, so when we say radiation here, we're really talking about stuff that radiates. Right? So waves that come from a source and sort of spread outwards. Specifically, electromagnetic radiation, that being like visible light, like colors, red, blue, violet, and such, but also ultraviolet light, infrared, radio wave, X-rays. There's a whole spectrum of this stuff, and astronomy uses quite a bit of it. So if you think about radiating waves, electromagnetic waves, you can sort of think about it as like ripples that radiate out on a pond when something drops into it or when it bobs on top of it. And so you have this picture here of the frog on the pond that maybe just landed into it, and you can see the ripples that are radiating out from where that frog landed. And if that frog were to like bob up and down, then it would continually make all these waves that are going outward. More broadly speaking, people use the term radiation to also refer to stuff having to do with radioactive material. We are not really thinking about that or using the term in that way. Pretty much specifically using it in terms of electromagnetic radiation or electromagnetic waves. And there's just a picture here of the sun in the ultraviolet part of the spectrum. And maybe just to point out that a lot of these pictures we're going to see, they're not visible light, not something you would see with your eye. They're colored, but the colors are just kind of picked in order to illustrate something about the information. So like this is ultraviolet light, and the colors are maybe the more intense or less intense areas of the sun in the ultraviolet spectrum. As it's noted here too, we can use those other parts of the spectrum outside of visible light to see things that we wouldn't normally be able to see. So I just need to give you a little bit of basic information about waves. So when you talk about a wave, one of the characteristics of that wave is going to be its wavelength. Like in this picture is showing, that's the distance, say, from the crest on one part of the wave to the next crest along. Or it could be from the trough to the next trough along. It's at the distance from one part of the wave until that wave starts to repeat again. Besides the wavelength, there's also generally the speed of the wave, like how fast it's propagating along. And for us, we're just talking about electromagnetic waves, and so those are propagating at the speed of light. And then finally, there's a property called the frequency. So that's the number of cycles that a wave will go through per second. And that frequency is very much related to the wavelength and the speed. The frequency and the wavelength are inversely proportional to each other. A longer wavelength is a lower frequency. A shorter wavelength is a higher frequency. And this is illustrated in this GIF here, where the frequency you can imagine as like how many waves are passing by a point, or how many crests of a wave pass by a certain point in a second. So with a very small wavelength, if these waves are moving at the same speed, say the speed of light, with a small wavelength, you get more oscillations, more waves going through per second. Versus the lower frequency, longer wavelengths, you get less waves per second. As I said, we're thinking about radiation, like this stuff that radiates out, that moves out from a particular place. And something that's important in astronomy is how spread out that wave gets as it moves away from the source. And this happens to be just a very general property of sort of space and geometry, and it comes up all over the place in physics, and that is what we call the inverse square law. It sort of relates to that example I used in the first lecture, where the further something gets away, the smaller it looks. In this image, we're looking at like a wave radiating out from the source, maybe like the sun, and that wave actually doesn't just go out in 2 dimensions, it goes out in 3 dimensions, so it's like this sphere that's expanding out from the sun. If you think about the amount of light that hits, say, right on that first sphere, right, it takes up this particular area that's shown in the first section. Think about then that light wave continuing to propagate out, it's expanding. And so once it gets to twice as far away, it's actually 4 times the area, right, the square of that distance increasing, 4 times that area larger now, And so the intensity actually goes down by a factor of 4. That wave has to spread out over 4 times the area. Or then if you think about from the first out to this third sort of sphere, if you look, it now has to spread out over 9 times the area. You got 3 times further away, then that area spreads out by a factor of the square of that, so 3 squared is 9. To kind of illustrate this point, if you think about the radiation that lands on the Earth from the sun, well, it turns out that there's about 1 kilowatt per square meter that lands on the Earth from the sun, square meter, something like that, right? About 1 kilowatt of power is landing on the Earth's surface coming from the sun. If the Earth was twice as far away, then that power, that radiation would have had to spread out over 2 squared 4, or 4 times the area. And so the power that would land on 1 square meter of the Earth at that distance is only 1/4 of a kilowatt. So it might be a little tricky idea, but more basically, just the further you are away from this source of radiation, the lower the intensity of that radiation gets. It's inversely proportional, or this inverse relationship. Now for a little bit more detail about the electromagnetic spectrum, or the range of electromagnetic radiation that there is. You might know visible light is just one portion of the electromagnetic spectrum. Right? There's a certain range of wavelengths of electromagnetic waves. That happens to be between a wavelength of about 400 to 700 nanometers. But if you go, say, to a longer wavelength, lower frequency of light, you get to infrared light. If you keep going to longer wavelengths, then you get to microwave, and then to radio waves. So there's just longer and longer wavelengths of electromagnetic radiation. On the other side of the visible spectrum, we would get ultraviolet light. Then if you go shorter wavelengths than that, you get X-rays, and even shorter, gamma rays. It's a nice little chart because it also gives you some images to think about or to understand the scale of the radiation, or how long the wavelength is in these different areas of the electromagnetic spectrum. So like for visible light, somewhere around the size of like cells, infrared, like the size of a pinhead, and then we're getting bigger microwaves like the size of actually insects, and then sort of people, and radio just even longer, larger wavelengths. On the other side of that, you're just getting smaller. Ultraviolet light is like on the size of molecules. X-rays, you're getting into like the size of the atom. Gamma rays, like the size of the nucleus. I mentioned in the last lecture as well that astronomy regularly is interested in the temperature of things. It turns out that each portion of the electromagnetic spectrum is also associated with temperature. So on the very long wavelength end, on the radio wave, we're very low temperature. We're associated with very low temperature. You get increasing. Yeah, I think we'll talk a little bit more about that in a couple of slides. And then finally on here, it actually shows something about the penetration in Earth's atmosphere, like which kinds of radiation actually get through Earth's atmosphere and land on the surface. And the next slide has even more detail about that. Let's look at that. So if you imagine all kinds of electromagnetic radiation, from radio all the way to gamma rays, coming at the Earth, right? They're going to hit the Earth's atmosphere. And it turns out the Earth's atmosphere is very nice because it blocks a lot of that radiation, and a decent amount of that radiation can be damaging to us. And apologies, this spectrum is actually reversed from the slide before. Can't really do much about that, sorry. All right, so on the left side, we're actually looking at gamma rays, the shortest wavelength radiation there is. On the right side, we go all the way out to radio waves, the longest wavelengths. And so we look at the gamma rays, they make it through some of the atmosphere, but they don't even make it down all that far. And once you get into the X-rays, even less penetration. Ultraviolet, most of that doesn't get through, but some of it actually does. That's what causes sunburns and cancers. Visible light, pretty much all the visible light gets through. Some infrared gets through, and then the microwave, somewhere in that infrared microwave is blocked a bit, or it gets down fairly low, but doesn't generally reach the surface of the Earth, or doesn't generally reach like sea level. Then we get into the radio waves. Well, radio is a huge portion. There's like very large portion of the electromagnetic spectrum. All right, so some of those radio waves get through and are going to land on the sort of ground level. They'll get down to sea level. But once you go to even longer wavelengths, they don't get through the atmosphere anymore. So this information is going to come back in a little bit later on in this lecture when we think about collecting electromagnetic radiation and where it's actually possible to do that. So if you notice, mostly it's visible light and some radio that actually makes it to ground level. So if we want to be able to detect or pick up, collect some of these other parts of the electromagnetic spectrum, well, we got to go pretty high up in the atmosphere or actually out into orbit. Certainly more on this later, but since we were just talking about the different parts of the electromagnetic spectrum and which ones we were able to see at sort of sea level versus higher up in the atmosphere versus in space, this is some example of pictures of the sky, but taken at different portions of the electromagnetic spectrum. So you're probably familiar with the constellation Orion. On the left is an optical picture, meaning it's visible light that was collected to make that image, right? So that's sort of like what you would see if you look out at the night sky. Probably a little bit more powerful than your eyes, but you can actually see a little bit of the Orion Nebula there, but right, that's basically the optical picture. That's visible light. In the middle, though, is X-rays, and maybe it seems a little bit similar to the optical one, but there's way more stars that are there. There's way more things that are visible there, and there's also ones that you don't really see as much, right? So some of the lower stars, or like along the bottom of the constellation of Orion, are barely even visible in X-ray. Right? They're not emitting a lot of X-ray radiation. The scale is a little bit off in the middle, right? So I tried to circle where Orion's belt is, where the three stars are in the middle one. And then finally, on the right here is the infrared image, where you don't really see the stars at all. All you're actually seeing is sort of the gas, the interstellar gas there. Back to thinking a little bit about temperature and wavelength. Like I said, different wavelengths are sort of associated with different temperatures. And that mostly comes about from something known as the blackbody spectrum. It's a difficult concept, so we're not really going to worry too much about it, except to say that all bodies, all matter, radiates electromagnetic radiation. It absorbs radiation and it emits radiation. And the temperature of the object has to do with where the peak in that radiation is going to be, what the most intense or largest quantity of electromagnetic radiation is going to come out of there. If you look at this graph, what it's showing is a wavelength scale along the bottom, and the different curves are material bodies that are at different temperatures. And then those peaks in each of those curves is showing where the most intense or the largest amount of radiation is coming from these bodies that are just radiating electromagnetic waves all the time. And if we look at the lowest temperature one on there is 3,000 Kelvin, pretty high temperature, and it radiates most intensely, or the peak of that radiation is at about 12,000 nanometers. You go up to say 4,000 Kelvin, now the peak has dropped down to a shorter wavelength of about 900 nanometers. Go up to 5,000, it's around 700. Go up to 6,000 Kelvin, it peaks out sort of in the middle of the visible spectrum at about, 500 nanometers? Something like that. So the overall takeaway here is that the higher temperature an object is, the shorter wavelength that it's going to radiate out at. Right? It's still radiating out at all these other wavelengths, but that peak, the largest amount of radiation, is going to come out at a lower and lower wavelength. And also something that we can take from this graph is about the power being put out by any of these objects. It turns out that if you look at the area underneath any of these curves, that is essentially the power, or sort of like the energy that's being radiated out from these black bodies, or from any bodies. Really, we'll think about stars a lot of the times. Right? So at 3,000 Kelvin, fairly small area, not a whole lot of power, right? But as the temperature increases, the area under the curve is getting larger and larger and larger. That is to say that a higher and higher temperature object, like a star, radiates out more and more power the higher temperature it is. And also, again, at a shorter and shorter wavelength, that peaks out. And then you notice that that higher and higher temperature is moving from sort of like red towards blue and violet, which is why when we look at stars, you can tell immediately that like a star that looks red is not as hot, lower temperature, than a star that looks blue. Since the main way that astronomy does what it does is collecting electromagnetic radiation, we need to be able to examine that radiation, and the more detail we can get, the better. So one way of thinking about how to get better detail, you could sort of think of like if you're looking at a picture and you're trying to make out something in the picture, but you can't quite see it. It's very useful if that picture is actually fairly large and you can zoom in, right? You can get closer and look at that in more detail, right? And then you can maybe figure out what that is. In terms of electromagnetic radiation, doing that sort of zooming in to different parts of the spectrum is what we call spectroscopy. And one way that you do that is by using some properties of light. One of the main ones is that light actually bends or sort of turns as it moves from one medium to another, or it can do that at least. You've probably seen that if you've ever had a prism and you try shining a light on one side, you see that on the other side you get a rainbow coming out. So that white light is actually made up of all those different colors, and when it hits the prism, that light bends, but the different wavelengths actually bend a little bit more or less depending on their wavelength. So violet light, or that wavelength that is violet light, 380 nanometers, is going to bend a little bit more than the blue light, and then so forth until the red, which is like does the least of that bending. So as it goes through this prism, all the light bends, but violet bends a bit more, red bends a bit less, comes out the other side, and there's now spread out. So white light comes in, and you actually get the spreading of these wavelengths on the other side. And that's one way of thinking of how you take light and sort of zoom in. You spread it out, and then you can see more detail in the spectrum. Like I mentioned, there's other ways of doing this sort of spreading out of light. Diffraction is another one, but we're mostly just thinking about refraction here. Light sort of bending, and it bending a little bit differently depending on its wavelength, so we can spread it out that way. The thing is, if we spread out light, and we kind of zoom in on the light, all well and good. But if light is always just this continuous spectrum, we can spread out as much as we want. It doesn't really make a difference. We don't gain any information by getting closer, because it all looks the same. So that's what we would call a continuous spectrum, which goes all the way from one wavelength to the next. Luckily, that's not what we see actually when we take in light from, say, like the sun or other stars and sort of spread it out. It's not a continuous spectrum. Early on in spectroscopy being applied to astronomy, when we start spreading out the light, say, from the sun, then we would do that, and we would end up seeing these spectrums that have dark lines in them. So it's not this continuous spectrum from red to violet. There's these bands, these dark bands, where you just don't get light there. It was also noticed that if you take like a gas of like hydrogen or sodium or something like that, and you shine sort of light through it, if you look at the light on the other side of that tube of gas, you see a similar thing, right? You see a sort of pretty broad spectrum, but there's these dark lines. And if you look actually off to the side, so like shining light through the gas, and you sort of look off to the side, you don't see this broad spectrum, you just see these particular lines. So people were starting to figure this stuff out or notice this stuff, I think late in the 19th century, where light just doesn't come in this continuous spectrum all the time. And we started to realize that for the light that's going, say, like straight through this gas, those bands, those dark spots aren't there because they're being absorbed by the gas. And somehow the molecules, the stuff that makes up the gas, is sucking up those bits or those bands or those wavelengths of the spectrum. And then when you look off to the side and you only see some bright bands, it turns out those are the same bands that are missing here. The further conclusion then is that the stuff that's in the gas that's absorbing at those wavelengths is also emitting the light at those wavelengths. And it turns out that different gases or different atoms, different elements will absorb and emit light at different wavelengths, or more broadly speaking, different patterns of wavelengths. Right? These wavelengths that are in the emission spectrum, right, that's a particular element. Because it becomes a very powerful tool, because if we look at the light coming from, say, a star, and we use spectroscopy and we spread that light out and we see where these missing wavelengths are, that can tell us something about what's making up the star, what elements are making up that star. So just to be clear, when you're looking at light that's come through this gas, or come through a cloud of gas and has these dark bands. That's what we call the absorption spectrum of that gas, or that element. When you're looking at the light that's just coming out of the gas, right? It didn't come straight through. It was actually created by the gas. That's what we call the emission spectrum. Here on the left, we actually see the absorption spectrum of the sun. So it's this whole spectrum from violet to red. Remember, this is just the visible part of the electromagnetic spectrum. But that whole spectrum, there's all these dark lines in there. Right? And that's information. That tells us about what stuff makes up the sun. And then if you look at the emission spectrum of different elements, different atoms, like I said, you see these patterns of lines. So sodium has like this pair of lines here, another sort of pair of lines here, a pair of lines there, right, at these different wavelengths. Hydrogen has these other ones. Calcium has a substantially more. Mercury has quite a lot too, right? But the patterns are all different. And in fact, they're unique to that element in a way. It's a little bit more complicated than that. But basically, that pattern of emission lines can tell you what element it is that emitted that light. So that's something that we call like a spectral signature. So you see this pattern of wavelengths, you know it's hydrogen. This is going to be a very brief explanation of why atoms have these emission lines, right? Why we can identify elements and atoms just by the wavelengths that they emit. To understand that, we need just a little bit of information about atoms, and then I'm going to throw a concept at you that probably very strange. Maybe it doesn't sink in, but give it a shot. As you might know, atoms are made up of protons and neutrons. Those make up the nucleus of the atom, the core of the atom, and electrons that sort of orbit around the nucleus. This diagram here shows the hydrogen atom, simplest atom that there is. It's a single proton that makes up the nucleus and a single electron that orbits around that nucleus. And in fact, the number of protons in the nucleus is what defines each element. So anything that has one proton in the nucleus, that's hydrogen. Anything that has two protons in the nucleus, that's helium. And so similarly to like the force of gravity that's binding or keeping the moon going around the Earth, there's an electromagnetic force between the electron and the proton, because they're oppositely charged objects, that's sort of keeping the electron orbiting the proton. It doesn't orbit in the way that the moon orbits the Earth, but you can kind of think about it as an orbit. Since it's just the number of protons in the nucleus that defines that element, you can actually have varying amounts of neutrons added to the nucleus, and it's still the same element. We call those isotopes of that element. Right? So here shown are a few isotopes of hydrogen. Hydrogen 1, that's kind of the most standard. Hydrogen, 1 proton. Hydrogen 2, 1 proton and 1 neutron. Gets a name, special name, deuterium. Hydrogen 3, 1 proton, right? Still 1 proton is hydrogen. And 2 neutrons. Also gets a special name, tritium. And then the sort of standard helium. Again, 2 protons makes it helium. The most common isotope of helium is 2 neutrons. 2 protons, 2 neutrons. And then you generally have 2 electrons to balance out the 2 protons. So as it turns out, it's sort of the shape of these orbits of the electrons that it determines the spectra, or like what those emission lines are going to look like, what those spectral signatures are going to be. And the shape of those electrons is determined largely by the makeup of the nucleus, how many protons and neutrons there are in there. As I said, these electron orbits are really not like the planetary orbits. Very different properties. One being that the electron orbits can only exist in certain configurations, and that depends on the makeup of the nucleus and also partly on how many other electrons are there too. An analogy to the solar system would be like, you can have a planet like Earth orbiting where it is, and you can have a planet like Mars orbiting where it is, but there's no possibility of any orbit existing in between. Either you're out here, you're in here. Nowhere in between. It's an odd thing because for our level, or at that macroscopic level, the normal level we exist, that's not a thing, right? We can exist anywhere in between there, it doesn't matter. For atoms, for electrons, in this very small world, it's strange, right? They can only be, like, say, out here or down here. Nowhere in between. So the picture on the left there is sort of a diagram of like the possible orbits that electron might be in. right? So n equals 1 is the first sort of orbit, so the lowest orbit. N equals 2, the next lowest, equals 3, the next. So that lowest orbit, we usually call it ground state. That's as low energy of electron as can exist in this atom. So imagine you have that electron in its lowest state, and along comes some electromagnetic radiation. And if it's just the right wavelength of electromagnetic radiation, then it can push the electron out to an outer orbit, or to a larger orbit, to a higher energy orbit. Right? So you go from like n equals 1 to n equals 3. Right? You bump that electron up. It can't be anywhere in between, but it can instantly jump up to that higher one. So that would be the atom absorbing that radiation. The electron, though, doesn't just like to sit there. Typically, it's going to very quickly want to drop back down to that lowest state, and when it drops down, it emits that light again, or it emits that electromagnetic radiation. So this is the sort of mechanism that gives rise to that absorption and the emission spectrum. So you think about light going through those gases, right? The electrons that are in the atoms in that gas are absorbing certain wavelengths of that light, and so those ones don't pass through. It's only when the electrons then drop back down to the lower energy levels that they'll emit those wavelengths, and you can see those kind of anywhere to the side. Like I said, very strange sort of concept. The GIF here does a decent job of showing this process where you have an electron in that lowest energy level, and you have that little green wavy thing is supposed to be like electromagnetic radiation. It comes in, and the electron can then absorb that just right amount of radiation and jump up to the higher level, right? And then that radiation's gone, it's been absorbed. And then again, pretty quickly, it's going to want to drop back down. So it'll drop back down, but it has to emit that same wavelength of electromagnetic radiation to do so. There you go, very brief explanation of the origin of atomic spectrum. The last main thing in chapter 5 that I wanted to mention then is about this Doppler effect. And this has to do with the wavelength that you will see or that you will hear. It happens with sound too, sound's also a wave, from a source that's moving. So we've all experienced this Doppler effect. If you're standing, say, on the side of the road and a siren's coming towards you, right, like a fire engine or an ambulance, as they're coming towards you, you probably notice, or maybe next time it happens, you'll notice that it sounds like a higher or a pretty high frequency when it's coming towards you. And then after it passes you, all of a sudden, it's a lower frequency. You've never thought about that before, then the next time there's a siren going by you, just take a second and think about it, listen to it. And so we call that the Doppler effect. If I was just standing there and the siren is just sitting there, then I'm going to hear a certain frequency, whatever frequency that siren's putting out. If that siren's coming towards me though, right, we think about it as putting out the sound or putting out these waves as like these crests that are coming out, right? Like the ripples in the pond comes crest to crest and crest. Right? That sound comes out like that too, comes out crest to crest to crest. If the siren's coming towards you, then the crests are sort of squished together. It will emit sort of one wave crest and then move a little bit closer before it emits the next one. So the wavelength that it was when it was stationary gets scrunched down. You get a shorter wavelength, which you end up hearing is a higher frequency. The opposite thing then just happens when it's moving away from you, right? It's moving away, it emits a wave towards you, and before it emits the next sort of wave crest, it'll move away a bit, and so that overall the wavelength stretches out. And we hear that as a lower frequency. This is a general property of waves, so it also happens with electromagnetic radiation. And it's the same thing. If the source of that electromagnetic radiation is coming towards you, the wavelengths that it's emitting are going to get shortened, they get scrunched together. And the terminology that they use in astronomy is shorter wavelengths is towards like blue in the visible spectrum, so we call that blue shifting, right? So when an object's moving towards you, its radiation gets blue shifting. Versus if the object's moving away from you, the wavelengths have gotten stretched out, and you're getting towards longer wavelengths, we call that red shifting, because red is the longer wavelength in the visible part of the spectrum. This then is my attempt to just sum up most of what we get out of chapter 5, which is what you can tell from the spectrum of light, or the spectrum that you get from, say, like a distant star. Well, we can tell something about its temperature, right? Remember that was from the peak wavelength, the peak emission wavelength from that source, tells us how high a temperature it is or how low a temperature it is. We can tell about the elemental makeup, like what gases make up that star or that object, right? And that's from those spectral signatures, the emission lines, and particularly the pattern of the emission lines. And then finally, we can tell something about its speed or its motion relative to us, and that has to do with the Doppler shift of those spectral signatures. So we see these particular spectral signatures, and they're very unique to a certain element, right? So if we see that pattern, we know that, say that pattern is hydrogen. But if we see that pattern at a shifted wavelength, say like towards the blue part of the spectrum, then we can say, okay, well that object is blue shifted, that means it's coming towards us. Or if we see that same pattern, but it's towards the red, more towards the red of the spectrum, it's red shifted, that means that object is moving away from us. And how much it's shifted tells us about the speed or the amount of motion going on there. So in summary, we can tell quite a lot just from collecting electromagnetic radiation. And I just want to note too that in modern astronomy, we don't just use electromagnetic radiation to observe stellar objects, stuff in the celestial sphere. We've realized that we can collect other things or analyze other stuff that's coming towards us. That gets a little bit tricky though, and for the most part, we still rely on electromagnetic radiation as sort of the largest component that allows us to do astronomy the way we do it today. So we're just going to focus pretty much on that. So given that looking at electromagnetic radiation can tell us quite a lot about distant objects, a sort of central task of astronomy is to collect that electromagnetic radiation and examine it. How we do that is usually with telescopes. Quickly though, before we talk about telescopes, just say something about what we normally see when we look out, or when we look up in the night sky. Apparently, there's about 9,000 stars, or objects, that we can see with our naked eye when we look up in the night sky. Right? And that includes the northern and southern hemisphere. So in just one hemisphere, maybe around 4,000, 4,500 objects you would see in the night sky. As it turns out, most of those objects, almost all of those objects, are within the Milky Way galaxy. That's the galaxy that we live in, that our solar system is in. But in the Milky Way galaxy, there are some billions of stars and objects there, right? And we only see 9,000. And the Milky Way galaxy is just one of billions of other galaxies in the universe. So there are like trillions, 1 trillions of objects that are out there for us to look at. I guess it kind of makes sense that evolutionarily we didn't really evolve to see distant stars, right? But we got pretty good technology and we came up with ways to see a lot more. So in terms of astronomical instruments, the ways that we collect electromagnetic radiation and then make it so that we can analyze that. There are 3 basic sort of components to doing that. One is the telescope itself, the thing that's collecting that radiation. And you can think about the telescope as sort of like a bucket, right? The bucket is trying to catch as much radiation as it can. And just like a bucket trying to catch rainwater, apparently the bigger the bucket, the more rainwater you're going to catch. That's why we end up needing pretty large telescopes in order to see more and more stuff. The next major component is a spectrometer. Right? So we talked about spectroscopy and the spreading out of light in order to sort of see more detail, examine in more detail. That's the other major component, or the second major component of an astronomical instrument. The last component then is the detector. The thing that kind of is able to take a log of the stuff that you collected, right, after it's been spread out to the detail that you're trying to see. And here are just some examples. This is this ground-based telescope, the world's largest refractor telescope, and the Hubble Space Telescope. It's actually an artist impression, but it's a nice picture. Yeah, when we use the term telescope sort of colloquially, then we're kind of including all of these components usually in that, right? The telescope is the thing that collects it, the spectrometer spreads it out, the detector registers all of that information, right? Usually we say telescope, you're kind of thinking of all those things together. So like I said, it's sort of like a bucket. You're trying to collect the radiation. The larger the bucket, the more radiation you can catch. In the language of telescopes, that opening is what we call like the aperture, right? That's sort of how large of an area are you actually able to pull in electromagnetic radiation from. Here we see the sort of two main types of telescopes. So one is known as the refracting telescope, and that uses a transparent lens, right, the lens at the top there, and we use again that property of refraction of light or bending of light as it goes through this medium or as it goes from one medium to another, like the air into the lens, and then the lens again to the air on the other side. So it bends, we're able to bend that light. The refracting telescope then uses that to focus a lot of light down to this small area, this very small point, the focus of the telescope. And then after that, maybe you have another lens, small lens, you should call it the eyepiece, which sort of pushes that light out again a bit in order for us to actually be able to see with our eye or to shine it on some kind of detector that will record the information or record what's coming in. The other main type of telescope is known as the reflector telescope because it doesn't use refraction, it uses reflection of light, meaning it uses mirrors, and curved mirrors. You probably know that mirrors are something that reflects light, light comes in, it bounces, and it comes back. If you use a curved mirror, then all this light that's sort of coming into the telescope, with just the right curve, you're able to focus all that light back up here to a particular spot again, to the focus. So in the same way that the refracting telescope curves it in like that, the reflecting telescope bounces and pushes it back all together here. There's actually two main types of reflecting telescopes. This, I think, is known as the Cassegrain type, where after you focus that light down, you use another mirror to push it off to the side, to reflect it to the side, and then to an eyepiece, where you can either look, or again, you shine it on some kind of detector that records it. The other type, I think, is the Newtonian one, where instead of reflecting the light to the side, you have a little hole in the first mirror, in the large mirror itself. You reflect it straight back down through that hole to, again, to an eyepiece or to the detector. We already talked about spectroscopy a little bit just a minute ago, so kind of jumping over that portion of the telescope or the astronomical instrument. Say we've already collected that light, we've spread it out in the way that we want, now we want to detect it, we want to log it. A little bit about detectors then, what it is we actually use, because these days you probably know that most sort of advanced astronomy is not done by just looking through a telescope anymore. Right? Most of the time that's done these days with these CCD devices, charge coupled devices, and those are in fact the same technology as what's in your phone's camera or in a digital camera. So these are just like arrays of like tiny, tiny little pixels, like millions of pixels on a square centimeter, that each are able to absorb the radiation that comes on them and sort of register how much it is and what wavelength it is, or maybe just how much it is. It depends on the kind of detector. So basically, very, very fancy and detailed high-resolution camera, or camera detector. So that's the CCD one. That's a lot of the modern stuff is. Over here, though, just shows some older ones, or older ways of detecting, or what the detector used to look more like. Back in Bray's day, it was still just looking at the sky and then drawing a picture, or writing stuff down. Right? So this is a page from Bray's observation of a supernova. Slightly more recently, we figured out how to take photographs using photographic plates, like chemical processes. You shine the light that you eventually got through your telescope onto this photographic plate, and depending on where the light hits, there's chemical reactions, and it leaves a print, a photograph. Right? So she's studying, I think it's like a star cluster or something. If you're doing astronomy, particularly if you're doing ground-based astronomy, you're building a telescope on the ground, you're trying to look up through the atmosphere and see stars, collect electromagnetic radiation, these are some things you got to worry about. For one, weather. Right? If it's always cloudy where you are, not a good place to do astronomy. For another, moisture, so water vapor that's in the air. It turns out that water vapor, or water molecules, absorb a decent amount of electromagnetic radiation, so you really don't want much water vapor in the air in a very dry place. Another pretty obvious one is light pollution. Right? If you're right smack dab in the middle of Los Angeles, you're not going to be able to do very good astronomy. A lot of the light that you're going to collect, a lot of the electromagnetic radiation is sort of washed out by the light from the city. And that can be visible light, so infrared light if you're trying to do that. And then finally, the atmosphere itself. So the level of turbulence in the atmosphere, right? You really want steady air. And the reason being is that turbulent air, or just air itself, can act as a lens. And so very turbulent air acts almost like there's a bunch of lenses in the air. And so they're kind of redirecting the electromagnetic radiation as it's coming through the atmosphere. So when it finally hits your detector, it's like it's a mess, right? You don't really know where it came from. So it turns out you really want very steady air, and that, I guess, comes from air that's flown very long distances over water. This is why places like Mauna Kea on Hawaii, on the Big Island of Hawaii, and the Andes Mountains in Chile, which are along the coast of Chile, right? Why these are very good places to do astronomy, or to have a telescope. However, you can get around all of this if you just get out of the atmosphere and you have a space observatory, something like Hubble or the Spitzer or the James Webb Space Telescope. The last, then, major component we're going to think about in terms of telescopes or astronomical instruments is the resolution that's possible with a telescope. The resolution is essentially like how small of an object can you resolve. You can think about it as like if there are two objects that are really, really close together, the resolution tells you how close together they can be, and you still are able to tell they're two objects. Typically, for modern astronomy, we measure resolution in something that's called an arc second, which is 1/3600th of a degree. And to give you an idea of how small that is, 1 arc second would be the equivalent of looking at a quarter, or how a quarter would appear to you if it were 5 kilometers away, about 3 miles away. 1 arc second. Very tiny. And that's just sort of the standard, right? A lot of telescopes these days get much lower than that, or much better resolution than that. As is shown here, the image is of the Very Large Telescope. Astronomers are very great at naming things. But this is known as the Very Large Telescope in Chile, again in the Andes Mountains in Chile. It's actually made up of 4 physically separate and different collecting telescopes, right? Like 4 buckets. So each one of those can get a resolution that's actually 0.05 arc seconds. We've also been able to do even better than that by sort of combining the power of 4 of these telescopes. We're combining the power of multiple telescopes together. I'm not going to talk too much about that, but yeah, just to say that we were able to sort of combine their observing power, and they sort of act like one much more powerful telescope. And can get an idea of that by the fact that when you combine all of their powers together, you sort of link them together, you're able to get a resolution of 2/1000ths of an arc second, more than 10 times better than the one by itself. I've kind of alluded to the fact that there are other kinds of telescopes, there are other ways to do astronomy. For the most part, I've been kind of talking about it in terms of telescopes where you could almost imagine you could still like put your eye up to the eyepiece and see what's coming in, right? So that's like visible light. We're doing astronomy with just the visible part of the spectrum. Very narrow part of the full electromagnetic spectrum though. And today we do astronomy with a whole range, pretty much portions, at least pieces from throughout the electromagnetic spectrum. This being sort of like an intro class, overview class. There's not a whole lot of time to go into great detail, but just to remind you that we do astronomy with all these different wavelengths, parts of the electromagnetic spectrum, and this image is pretty useful in understanding that, or getting an idea of the value of seeing in all those different parts of the spectrum. So this is the same part of the sky, the Crab Nebula, but it's images in 6 different parts of the electromagnetic spectrum. So on the upper right here is visible light. If you're able to see it with your eye, it would look something like that. But we can also image it in infrared radiation, right? Or in that infrared part of the spectrum. And again, once it's outside of the visible range, these colors are not real colors anymore. These images are colorized to elicit some information about the image. A lot of times to do with the temperature or the relative intensity of those waves. So we got infrared, you go to even longer wavelengths, this is radio. On the other end of the visible spectrum, that's the Crab Nebula in ultraviolet light. There's the pretty interesting one in X-ray, where you actually see in a little bit more detail what's in that nebula. It's kind of like a star that I think exploded at some point. I'm pretty sure that Crab Nebula is a planetary nebula, which means it's a star that has kind of exploded at some point in the past, and this is just gas that was pushed away from that star. I think that is, at least. Don't quote me on that. So that's X-ray, but you can go even higher into X-ray, and there's other kinds of things you get to see. Yep, and that's it for chapter 5 and 6. Until next time.